Hello again. This is our first video lecture for Chapter 9, Video Lecture 9.1. Chapter 9 is entitled Linear Momentum, although there are a lot more ideas than that in the chapter, but that's kind of the cornerstone new idea. We'll get to that in a couple of sections. This lecture is about Chapter 9, Section 1 in our book, which is entitled The Center of Mass. This is an important point in the extended body called the center of mass. And in this chapter, we're going to need to know about that. So the first key idea to talk about is how you determine where the center of mass of a system of particles is located. What we've been doing all the way up through Chapter 8 has been studying objects that we have been calling particles. The motion of particles. And as a reminder, what that meant was either it was very, very small, like a particle, or more commonly, it's not necessarily a small thing, but at any given instant, every single piece of that body has exactly the same velocity, like a big block sliding down an incline, or a big sphere swinging on the end of a rope. Okay? Then the thing can be called a particle. And we draw it in free body diagrams, like a dot, like a particle. But now we're going to admit that there are situations when objects cannot be treated as particles, right? And I want to talk about that. When can an object not be treated as a single particle? At least not to study all of its motion. There are two main situations that, if either applies, means you can't treat the object as a single particle. That's when the object rotates about what's called an axis of rotation, or when it's a deformable object and it changes shape as it moves. We're going to focus more on the first situation, and we're going to have an object that's, at least soon, we're going to have an object that's rotating about an axis. Let's explain why you can't treat a rotating object as a single particle. I'll show you two reasons. First, a photograph. This photograph shows a person holding one baton, but has just thrown a second baton into the air, and upon throwing, twisted the wrist so that it's rotating, this baton. And we took a snapshot, as you can see. And at the instant we took the snapshot, one end of the baton has a velocity directed that way, and the other end of the baton has a velocity directed that way because of the baton's rotation. Now remember, velocity is a vector with both a magnitude and a direction. Those two velocities might have different magnitudes, but even if they had the same magnitude, they definitely have different directions. So the different parts of a rotating body do not, at any given moment, have the same velocity. So you cannot treat a rotating body like a single particle and just do all the analysis we have done up through Chapter 8. So now we're going to figure out what to do. Well, let me motivate a little more about what we're going to do by showing you a Wiley Plus simulation. Okay? Now, it's rather schematic, but what you've got in this simulation is a baton with sphere 1 in red and sphere 2 in purple, and a line which represents the handle part of the baton. We're going to assume all the mass in this baton is in the two spheres, and that the handle is a rigid object but has negligible mass. And right now, with this slider at the top labeled M2 over M1, I can control the ratio of the masses of spheres 1 and 2, and right now, since that ratio M2 over M1 is set to 1, the two spheres have equal mass. The x-axis is horizontal and the y-axis is vertically upward. And all we're going to do when we run the animation is see the motion of the baton. Now what we're going to do is we're going to have our baton thrower, when they release it from the origin here with an initial velocity, they're also going to give it a twist with their arm so that it's going to rotate, as you often see baton throwers do. but we're going to throw it as a projectile. And I want us to watch the trajectories of the two spheres. Now remember, we learned in chapter 4 for projectile motion of a particle, the trajectory is a parabola. Let's see what the trajectories of the two spheres are now. So what I have to do is just run the animation. Okay, now actually you have three trajectories traced out there. The red curve is the trajectory of sphere 1. The purple curve is the trajectory of sphere 2. Those are complicated curves. To probably figure out how to draw them as what are called parametric curves, ask your calculus professor, or take Physics 310. But we're not going to deal with those, describing those curves mathematically in this class. I hear you taking a breath of relief. They're not parabolas, yes? The red curve and the purple curve, not parabolas. But wait, the blue trajectory, that is a parabola. That is a parabola just like chapter 4. Where's that coming from? Well, it may be hard to see, but it's coming from the point, there's a little point marked with an X on the rod, which in this case, that point is exactly midway between the two spheres. That point of the baton did follow the parabolic trajectory that we would have studied in chapter 4. Now let's reset. And let's change the mass ratio. Let's make the purple sphere, sphere 2, much more massive. Well, twice the mass of sphere 1. You'll notice that special point marked with an X has moved a little closer to sphere 2. Now we throw the baton again, and now let's watch the trajectories. Well, the lighter sphere, maybe as you might have predicted, follows a bit more complicated wild trajectory. The heavier sphere, the more massive one, is a somewhat less complicated trajectory, but neither of those is parabolas. But that special point marked with an X still moves along a parabolic trajectory. Let's reset, and let's go to the other extreme. Now let's make M2 merely 0.1 of M1, 10%. Now notice that the special point marked with an X is very, very close to sphere 1. And now throw the baton. Very interesting. Spheres 1, the trajectory of sphere 1 is not too bad. The trajectory of sphere 2 is a mess. But that special point marked with an X follows a parabola. Something is clearly special about that point marked with an X. That point has the simplest motion of all. That point we ought to at least be able to describe the motion of. That special point that has moved around as I've changed the masses of the spheres is called the center of mass. And as I change the mass slider here, you can see that point called the center of mass move. In fact, it tends to go towards the more massive sphere, if you've noticed. So what I'm trying to motivate for you is, when I have a body that's moving in a complicated way, so let's say with some kind of rotation, then the motions of all the individual particles might be quite different from each other, but that special point called the center of mass, that's going to move in a somewhat simpler manner, and that's what we're going to focus on at first. Just describing the motion of this special point called the center of mass. Okay, so now back to our slides. Hopefully I've motivated for you that this point called the center of mass on an extended body is important. Let's say some more about it. The center of mass, denoted COM, of a system of particles moves as if. Okay, here are two important points. All the mass of the system were concentrated at that center of mass, and all external forces acting on the system are concentrated at the center of mass. That's how we're going to determine the motion of the center of mass. We're going to assume, at least to determine the motion of the center of mass, that all the mass is located at the center of mass, and all the external forces acting on the system are acting at the center of mass. But before we can do any of that stuff, we have to just find where the center of mass is. So we need to know how to locate the center of mass for a system. We're going to start with a system that consists of capital N particles. And the total mass of all of them is big M. If that's our system, and I'm going to show you an example of what I mean in just a minute, but my system consists of capital N objects that themselves are particles, and the total mass of all n of those particles together is big M, how do you find where the center of mass of that system is located? Located, just what are its coordinates in space relative to a chosen coordinate system with a chosen origin? I'm going to list XCOM and YCOM. How do you find the X coordinate of the center of mass? And how do you find the Y coordinate of the center of mass? Note the 3 lines here for each. This is how you define where the coordinates of the center of mass are. You do in math and physics what is called a sum, an addition, S-U-M. And that symbol right there is a capital Greek letter sigma. And it's used in math and physics to mean a sum, an addition. Okay? And what is it that you sum? What is it that you add? The things inside here, following the sum symbol, are the things to be added. So here's what you do. You go to each particle in your system. Remember, there are capital N of them. You go to them one by one. Maybe you put a little label on each one. Your particle 1, your particle 2, your particle 3, up through N. You go to each one at a time. Particle 1, what's your X coordinate? That's what this means. Xi, where I means is an index that denotes a label for the particles. And you multiply the X coordinate of that particle by this ratio. The mass of that particle divided by the total mass. And then that will just be a number, and you do that for particle 1. You take M1 over M total times X1. Then you go to particle 2. What's your X, please? And what's your mass? Then you take M2 over M total times X2. Then you go to particle 3. What's your X and M, please? Then you take M3 over M total times X3. And you go on down the line until you do all 10 particles, and you add those numbers up. And the result will be the X coordinate of the center of mass. Then you play the same game with the same particles, but working with their masses and their Y coordinates. Okay, back to you, particle 1. What's your Y coordinate? Then you take M1 over M total times Y1, and do that for all the N particles and add them up. And that will be the Y coordinate of the center of mass. That's going to be how we're going to focus for a while here on finding the center of mass of a system of N particles. Again, when you're done, you will have one number for the X coordinate of the center of mass, XCOM, and one number for the Y coordinate of the center of mass, YCOM. That means if you imagine that your system resides in an XY coordinate system, then there will just be some point that will be at the coordinates XCOM, YCOM. And that point, that's where the center of mass is. That's where it's located. Okay, so as I note, the center of mass can be plotted. I just marked it, like there's where it might be. It can be plotted in the XY plane. And what if the N particles are all moving around? If they are, then the location of this center of mass might very likely be moving too. So the center of mass can move around. If the particles are moving, possible. Here's something else to note. There doesn't have to be any actual physical mass at the location of the center of mass. I mean, there are N particles here, apparently. But this place I've marked as COM doesn't have to be any actual mass there. Still, that point's the most important point on the object, the center of mass. And, as I actually showed you on the animation, the center of mass is biased toward the particles with the largest mass. Why? Because back here in these equations for calculating XCOM and YCOM, what we're doing, no pun intended, is called a weighted average of the X and Y coordinates. If I just gave you capital N X values and X asked you to take the simple average, x AVG, the arithmetic average, you would, this is one way to do it anyways, you would sum with your index I going from 1 to n, sum over the particles. You would take the x coordinate of each particle and you would weight it by 1 over the number of particles. That's equivalent to adding up and dividing by the number of particles. That's called a simple or unweighted average. But our weighting factor here is more complicated than just 1 over the total number of particles. Our weighting factor is the mass of the ith particle over the total mass. And different particles might have different masses. So this factor in the parentheses can be different for the different particles. And for a particle with more mass, a bigger fraction of the total, that fraction is going to be bigger. And so the x-coordinate of the more massive particles have more weight in calculating XCOM. They're more important. Okay? So these are called weighted averages of the x and y coordinates. And so the COM will be biased towards where more of the mass is. We saw that in the animation. Whichever sphere I chose to have the larger mass, that point marked with the x that was the center of mass was closer to that more massive sphere. All right, now I want to do a more specific calculation, a more specific example of calculating the location of the center of mass of an n-particle system. And I'm going to do that by using an animation, which I will show you in a second. But I'm going to take a system with capital N equals 4 particles. All right, now let me get my picture here, and then go here. Okay, now you're seeing an XY coordinate system with X in meters and Y in meters and an origin, and 4 particles, 4 spheres. A blue one in particle 1, a red one, particle 2, an orange one, particle 3, and a black one, particle 4. And they are currently located in the XY plane at particular coordinates that you can actually see at the top of the animation, right? You can see the X coordinate for particle 1, X1, 2 meters. Y coordinate of particle 1, Y1, 0. And that determines where the blue particle is sitting. You can see what X2 is 4 meters, Y2 is 0. Excuse me, Y2 is 2. Okay, I think I just, for some reason, lost. I'm going to have to pause. Okay, hopefully we're back and recording. Had a little technical issue that I had to deal with here. We're going to resume. Okay, now, the other particles, maybe can't see all the coordinates currently. It's okay. I will just tell you, X3 is negative 2 meters, Y3 is 1.5, X2 was 4 meters, and Y2 was 2 meters. And X4 is negative 0.5 meters, and Y4 is negative 3 meters. So that is our system of 4 particles. Okay? I will also tell you what the masses are. Blue particle, mass 4 kilograms. Red particle, the mass is 3 kilograms. Orange particle, mass is 2 kilograms. And the black particle mass, 1 kilogram. 4, 3, 2, and 1. And the bigger ones have the bigger mass. Okay, so let's go through calculating the XCOM and YCOM, the X coordinate of the center of mass of this system and the Y coordinate. And then we'll show it in the animation, okay? All right, now, get back to the screen. The way we calculate XCOM is we do a sum. I going from 1 to the number of particles, in this case 4. We take the mass of each particle divided by the total mass of all of the system, and then multiply by the X coordinate of that particle. All right, so I'll list here. M1 is 4 kilograms. M2 is 3 kilograms. M3 is 2 kilograms. M4 is 1 kilogram. And big M, the total mass, is 10 kilograms. Okay, so here we go. The calculation to find the x-coordinate of the center of mass of this system. Particle 1, start with that. We take the mass of that particle, 4 kilograms, divided by the total mass of all of them, 10 kilograms. Notice the units of kilograms cancel. Then I multiply that by the x-coordinate of particle 1. I will just tell you that's 2 meters. So notice how I'm putting the units. That's the first term in the sum, particle 1. Now we do the same thing for particle 2. We take the mass of particle 2, 3 kilograms, over the total mass, 10 kilograms, and I multiply that by the x-coordinate of particle 2. I will tell you that's 4 meters. Now we go on to particle 3. Mass, 2 kilograms, total, 10 kilograms. X-coordinate of particle 3, I will tell you, -2 meters. And then lastly, for particle 4, M4, 1 kilogram, M total, 10 kilograms, X4, -0.5 meters. Notice all those kilograms cancel, and my result, since it's a location, has units of meters. And now you go to your calculator, and you do that calculation very carefully. But notice, particle 1 has the largest weighting factor. This number in front is 4/10. Particle 4 has the smallest weighting factor. The number in front for it is 1/10. So the x-coordinate of particle 1 is more important than the x-coordinate of particle 4. But in any event, you just go to your calculator and carefully work this out, and you get XCOM is 1.55 meters. And you have located the x-coordinate of the center of mass. Now, we're going to calculate YCOM, the y-coordinate of the center of mass. So again, we do a sum, another sum, I going from 1 to 4. We take the mass of particle I divided by the total mass, and now we multiply that ratio by the y-coordinate of each particle. So let's do it. I will go ahead and not write the units there since we know they cancel. 4/10. Now the y-coordinate of particle 1 is 0. It's on the x-axis, so that's what that goes there. Plus 3/10, and the y-coordinate of particle 2, 2 meters, plus 2/10, the y-coordinate of particle 3, 1.5 meters, and then plus 1/10, and the y-coordinate of particle 4, -3 meters. And then you just go to your calculator, and you see what this gives. And it gives 0.60 meters. So this tells me where the center of mass is located for this 4-particle system that was shown in the animation, right there. So now I'm going to click the button up here, Show Center of Mass, and it's going to mark it with an X, COM, and it's got to be at X coordinate of 1.55 meters and a Y coordinate of 0.6, and it's going to draw an actual position vector for the center of mass. That's going to be labeled R arrow COM. Like that. R arrow COM. That's the position vector of the center of mass. It's a vector that points from the origin of the coordinate system out to where the center of mass is located. So let's click this button up here. And there it is. There's the point marked with an X. Its X coordinate is 1.55 meters. Its Y coordinate is 0.6 meters. And then the position vector for it goes from the origin out to that point. And it's labeled RCOM. And if the particles move, then the position vector of the center of mass moves. Notice the center of mass vector is biased towards where the more the mass is. Since the two particles 1 and 2 are the more massive, it's over towards where they are. And if I move around particle 1, watch the center of mass more or less follow me. Yes, the center of mass is paying quite a lot of attention to where that massive particle is. Conversely, if I move around particle 4, the least massive particle, the center of mass is like, yeah, okay, yeah, I notice you're moving, but I'm not that worried about you. Okay? So, as the particles move, the center of mass can move. No doubt about it. All right, now, sometimes we will have to deal with simply what I'm showing you here, a system of some number of particles. But a lot of the time, what we're going to have, let me now go back to my slides, is at what I would just call an extended body. How do you deal with an extended body and finding the center of mass of such a thing? Okay, let me show you how we're going to deal with that. This figure shows an object that is made of 3 uniform thin rods. Uniform means that each rod has its mass spread out uniformly along its length. And the length of each rod is the same, L, 22 centimeters. And they have been welded together, if you like, to form an inverted U, an upside down U, and they've been positioned in an XY coordinate system with one side butted up against the origin in the y-axis. These two over here and here are the same. They're called the vertical rods. They each have a mass of 14 grams. The horizontal rod up here looks like it's thicker, and sure enough, it has more mass, 42 grams. No rod down at the bottom end there. It's an upside down U. We are to find the x-coordinate and the y-coordinate of the center of mass of this thing. That's our system. Okay? So how do you do that if those are extended bodies? Not like the particles I was just showing you. As long as they're uniform, then you can treat each extended body as if all its mass is at its geometric center. Okay? So you reduce each rod to a point particle with all its mass at its geometric center, if they're uniform. So the vertical rod on the left is reduced to a point with all 14 grams of mass exactly at its center. Similarly, for the other thin vertical rod, all its mass is reduced to a point of 14 grams at its geometric center. And the same thing for the heavier horizontal rod. All its mass of 42 grams is located at its geometric center. And let me call this one up here M1. So M1 is 42 grams. And let me list its coordinates. That is to say, what is X1? What is Y1? For that mass for the thick rod. Well, that red dot up there is at the geometric center of the thick rod. The thick rod has length L with its left end at the origin, so the x-coordinate of that dot must be L over 2. The y-coordinate, since that horizontal rod lies along the x-axis, is 0. So that's the particle that represents the mass of the thicker rod. Let's say this one over here is particle 2. So M2 is 14 grams. I'd like you to take a second and figure out for yourself the coordinates of that center point there, because that's where that mass is. What are X2 and Y2? Feel free to pause the video, but please think that out for yourself. What's X2 and Y2? Okay, did you say X2 is 0? Right? Because the coordinates of this red dot, for particle 2, on the y-axis, so the x-coordinate is 0. Now this rod is along the y-axis, butted up against the origin, so the y-coordinate of that dot, did you say, watch out, negative L over 2? Right? Look where the origin is. This is negative. Y2 equals negative L over 2. Okay, here's particle 3 with a mass m3, which is also 14 grams, excuse me. Now, what are the coordinates? x3 and y3. Figure that out for yourself and then come back. Okay, did you say x3 is L and y3 is negative L over 2? Okay, and what's the total mass? Big M. Well, that's M1 plus M2 plus M3. So that's 42 plus 14 plus 14. That's 70 grams. Okay, so we want to find where the center of mass is. What is XCOM and YCOM for this thing? Give you a little bit of a hint. If your object has any what's called line or axis of symmetry, the center of mass has to be on that line or axis. And a line or axis of symmetry is a line that the whole thing could be reflected or folded about, and it would look the same. So for example, for this inverted U, if I draw a vertical axis going through that midpoint in the horizontal rod like that, then the thing is symmetric about either side of that axis, right? This is called a symmetry axis. I know the center of mass has to be somewhere on that, which means the x-coordinate is L over 2, right? What's the y-coordinate? Well, it's going to be closer to where the mass is, and the horizontal rod has more mass. So my guess is that the center of mass is at x equals L over 2, and at a y value somewhat nearer to that horizontal rod. But we can't just guess. Let's actually go through the calculation and see what we get. So XCOM is sum I going from 1, in this case, to 3. Take the mass of each particle, divided by the total mass, and then multiply by the x-coordinate. So let's see what we get. We've got 3 particles. It's those 3 red dots. Okay, for particle 1, what's this mass ratio? What's M1 over M total? 42 over 70. I can leave them in grams here because they're both the same units, and it's a ratio. And what's the x-coordinate for particle 1? L over 2. All right, plus. Now particle 2, what's the mass ratio? M2 over M total, 14 over 70. What's x2? 0. Plus particle 3, what's the mass ratio? 14 over 70. What's x3? L. So when I worked that out, I got 35 over 70 times L. But you check that for yourself. That is 1/2 of L. 35 over 70 is 1/2. So as I predicted, the x-coordinate of the center of mass is at L over 2. L is 22 centimeters, so L over 2 is 11 centimeters. Okay? Now do the same thing to get YCOM. Mass ratio times y-coordinate. Particle 1, 42 over 70. What's y1? 0. Plus particle 2 mass ratio, 14 over 70. What's y2? Careful, negative L over 2. Plus particle 3 mass ratio, 14 over 70 times y3. Another negative L over 2. Now, you do that carefully. Notice the first term is 0. You will get 14 over 70 times negative L. That turns out to be exactly negative 0.2 times L, which is negative 4.4 centimeters. So that's where the center of mass is, at L over 2 and negative 0.2 of L. Okay, so on the symmetry axis and up a bit closer to the horizontal rod because that had more mass. Okay, if you want more examples of figuring out where the center of mass is located, read Chapter 9, Section 1, and look at the examples. And you'll find some more applications of finding the center of mass of extended bodies. But that's what we've talked about for this video. And next we'll be talking about how you determine the motion of the center of mass. But that's all for this video.